Good day, folks. Just an update on things. I'm still alive. Just been waiting for some parts and stuff to come in, and as you see, things are starting to come in. So nothing specifically built yet, but what I like is always modular, where I already have my PCB builds and stuff like that, because sometimes I shake and stuff. So essentially, I'm in the direction of the Don Smith stuff here. So what I want to experiment with is just at higher frequency. So here's basically going to be one of my driver coils. And this one here is going to be the one, basically the step-up air coil. And basically, if you've been following me, it was about the last thing. It was I talked about the generator displacement current with capacitors, but what I didn't get into details was the mechanism that actually precharges the capacitor, right? Under the assumption that everybody knew whatever it is you want to use, high voltage, high generator, whatever efficient way you want to charge that capacitor, of course you need to originally charge it somehow first, right? I just assume everybody knew that. So people were getting confused and not figuring out where, this half charge that I was talking about was coming from, and basically accusing me of bad math. But essentially, yeah, I just assumed that people would naturally know that. You pre-charge the capacitor first. Some people wouldn't consider that a quote-unquote free energy source because you had to pre-charge it. But depending on how you pre-charge it, it may very well be, right? So if it's driven by a Don Smith-like high-frequency energy system, it may very well be. So again, just assumed everybody knew that, but some people didn't, and they tried calling me out on it. But the point is, the displacement current effect, using basically transformers to capture it with capacitor dumps back and forth works. But, that's basically a transducer method. And what I want to do is work on, now the generation, the high frequency interaction like Don Smith was doing. So essentially, this is going to go this in here, wire all this up. Now I'm going to try with some medium power first, higher frequency such as this thing here. It's not really wired right. But what I got here is because high frequencies make noise and everything, and without being high tech, you want to use mechanical. So this is a mechanical 110 volt DC chopper. So it's essentially a relay, but one that could work on modest duty cycles, anywhere from 200 to 2,000 hours. So unlike a ringing relay, which would wear out if you would run it like this after a few minutes, these run typically at around 60 to 100 hertz, and they'll run at various input powers. This one here, I'm going to show you here, 110 volt DC input. So my idea is charge a capacitor, or one of them anyways, real fast, and this could be the analog switching that could essentially self-dump. And it doesn't matter if it's near high voltage fields and whatever. So good to prototype with. But this generates, of course, noise, a lot of noise, high frequency random noise. So this is where chokes come in, right? So before sending right to your output load here, here's the filter coil like Don Smith was doing here. So what's nice about this, everything I like is on modules, right, already ready for me. So these are variable capacitors to tune the choke. So there's one choke and another choke here. So we would pass the switching through this one, and this is all BNC inputs. And you can see here additional filtering LCR networks to really get DC at different ports here. So let's say I want this one here runs my load. I could reserve this one here on this one here to charge my battery like Don Smith was doing, while this one here runs my load, okay? So of course this would be in the output of the capacitors, which I don't have yet, or we're still working on this, I'm just trying to figure out how everything's going to work. These are going to be additional RF chokes if I need them for filtering. And of course, something that I never thought I'd get, which is very novel and interesting, I should say. The nonlinear ferroelectric capacitors, which is usually military and high-tech industry use, science and research, and that's right here. It's actually a dual capacitor. It accepts RF here, and on the output is a pulsed depending on the frequency, actually higher output. But that's because this is highly piezoelectric. You see on the other side here, this big, you'll see it here, tiny non-linear capacitor here, very tiny electric plate compared to the dielectric, which is a very thick barium titanate plate. So the RF tickles that, triggers a very massive piezoelectric. So it's dual frequency, so F1, F2 independently. And here's a little filter and rectifier, which goes so you get your pulse. So this gives you a super clean and rectified and even amplified F1 and F2, you know, which could be useful for frequency mixing like Tom Bearden was talking about, you know. So there's an F3 that appears, right, in a nonlinear medium. So essentially this is what I want to do, use it for feedback, you know. So again, usually for military, very high-tech applications, but this is, I think, maybe part of the puzzle. So use that to help anyway, somewhere along the line here for some RF feedback through the piezoelectric. You know, this is all stuff you'd see right from far, and people have the plates, and like Don Smith, they don't get into the details, and people will think, oh, it's just one of the capacitors, because that's what it looks like from far if it would just be mounted there, right? But now that I showed you inside, it's a capacitor, all right, but nothing like what you'd think, right? So this is actually running the same way as Don Smith runs his capacitor, where on one side, you don't see it here, but the RF goes on the far side, and on the other side of the glass, which is not really glass, which is the barium titanate, is the other receptor. So it clones the state, but with the addition of the piezoelectric response. It gives you a super clean, because some applications require very precise feedback, so this is a good way of doing it. But they don't tell you everything else it can do, right? So yeah, so we're getting there. I'm gonna eventually start mounting and testing all of this, frequency ranges and whatnot, and still waiting for some more parts to test. But just to show everyone that this is all in the works, and I'm getting there. And until next time, and have yourselves all a great day, folks. And this was just an update to show everyone that people are getting, you know, worried. So here you are. Enjoy, everyone. Thank you.